Hello, I'm Matthew Calagaro, and I'm one of the instructors from the Autonomous Racecar course. For the last 4 weeks, students have been programming their cars to perform a variety of tasks, starting with some introductory tasks such as following lines and detecting objects, and building up to some more advanced challenges, such as performing wall following, basic path planning, and even sensor fusion. They've been performing all these tasks on 2 versions of the car. First, every student was mailed a physical car that they've been programming to drive around inside of their house, and they've been working in a simulation environment, which helps with the virtual aspect of this course. Today, the students are going to be presenting to you 2 major accomplishments. First, teams have been doing research and exploring individual topics that they'll be telling you about today, and they've all been competing in time trials and a final Grand Prix race.
Okay, great. Let's start the video for Team 1.
Hello, I'm Grace.
Hey, I'm Weija.
Hi, I'm Lasia.
Hi, I'm Emma.
And welcome to our presentation.
We were inspired by our main competition and instructor Matthew's presentation about the process of making the race car simulation, so we wanted to recreate a simpler version of our own to demonstrate today, which has autonomous AR marker comprehending, color distinguishing, contour detecting, line following, and cone slaloming. In addition, we spent most of the course working in a race car simulation, so we were excited to have the opportunity to program the real hardware. In the simulation, there are much fewer external factors which can interfere with the race car, while in real life there are many more areas for error. And we were curious to see how effectively we could implement what we would learn throughout this course into the real world.
Our plan for this project was to create our own level on Unity, which includes line following and cone slaloming sections. Then we would program solutions that work both on the simulation and in real life. The first part of the problem was to create the Unity simulation. There were a couple of elements we needed to use in order to create a lab. First, we added a map with colored lines that the race car would follow using a color camera. We then added 2 cones right after the line following section, so the race car will slalom around them. Finally, we created 2 AR markers. The first one was placed right in front of the race car's starting screen and has a colored border that represents the correct colored line to follow if the path diverges. The second marker was placed in between the line following and cone slaloming sections, telling the robot to switch into the cone slaloming mode. Let's run the code.
To complete the track, we had 2 components to complete, the line following and the cone slaloming, basically looping around the cone. For the line following, we used AR markers to choose what color we should follow. We used a color camera to get a contour, or basically a chunk of the color we needed. A race car would then use the center of the contour as a reference point to follow. The next component is cone slaloming. We would use the color camera to detect a contour of the cone, and then use a depth camera, which basically gives us the distance from a respective point to rotate around the cone when close enough. While the code worked adequately on the simulator, getting it to work in real life was a whole different challenge.
Once we had all of the code in the simulator running smoothly, we shifted our focus to getting the code all on the physical race car. One of the biggest differences between using the simulator and the physical car was color detection. In order to recognize objects based on their color, which is really useful for things like line following and cone slaloming, we had to find the color ranges of our color tape and cone. While in the simulator, we could use a small color range as there isn't much variation in the preset colors. The physical camera had to be able to detect a larger range of colors as things like shadows and lighting affect what the camera sees. In addition, another issue we ran into was camera lag. Due to some software issues, the camera on our physical race cars were very slow, which caused our car to veer off the lines that we had taped. After a lot of setup and numerous updates, our RealSense camera still had lag. We tried running it with a default speed, but as you can see here, the camera just doesn't catch up. We realized that if we run the code in short bursts and allow the race car to adjust itself in time, we could run through the line following smoothly.
Thank you for watching our video.
Thank you so much, Team 1. We don't exactly have time for questions, so if Team 2 could
Hello, everyone.
make their video available.
Honey Nut Cheerios team presentation. My name is Evan.
And my name is Sean.
My name is Atanj.
And my name is Ro.
And my name is Jaden.
So when thinking of our project idea, we had a large amount of them. However, we had to settle on one final one. So here's what we knew. Autonomous race cars are cool. Roller coasters are cool. Car jumps are cool. And by this point, it is obvious.
So that was the final project idea we chose, autonomously trying to make our car go in a roller coaster type course.
During class, we used the race car in a simulation made in Unity. As you can see with these images, all levels are made in Unity and the structures can be made in Unity or with 3D modeling software.
We faced multiple problems when originally designing our course. The first one was actually trying to create the ramp and loop.
We tried to make the ramp and loop in 3 different ways and wanted to continue to choose the best one. First, we tried using the simulator to create a ramp and loop.
However, it wasn't as easy as it seemed. Since Unity isn't a modeling software, creating the loop required creative solutions and was more difficult than we thought. We tried to use pre-made ramps and arrange them in a way we needed, but when the pre-made ramps weren't what we wanted, we tried aligning a bunch of rectangular objects to make a ramp. That didn't work either.
We tried using SolidWorks to create the ramp. However, we encountered challenges there too, such as trying to make the ramp smooth so the car could actually go on it. Also, we had to make sure the ramp is on the correct scale when we put it in the simulation.
And finally, we tried to use Blender to make the loop. We encountered the same problems we did when using SolidWorks. Furthermore, importing it into the simulation turned out to be harder than we expected.
Another problem we faced was trying to put a colored line on the track for a car to follow. We tried to tackle this problem in different ways also.
In Unity, the colored lines cannot be put on straight onto curved surfaces, so we had to break up the line into tiny segments and put it onto the loop.
In SolidWorks, we had to do something similar. We had to use small-sized rectangles of the same color and put them in a line pattern.
In Blender, we tried to put a stripe pattern through the middle of the loop that could be used as a line for the car to detect it.
Eventually, we found a final solution. We decided we would use a mix of all 3 pieces of software. This was because each piece of software had its own advantages.
SolidWorks allowed easy development of the ramp because of its functions. Blender allowed easy development of the loop because it mostly works in polygons. And Unity, because of its easy segmentation of the lines, was used for the lines.
So this is our final race car course. We have a steep ramp leading into a loop. At the end of the loop, we have a ramp which our car jumps off of. Finally, we have a green cone to signify the track is over.
Here's a snippet of our code. We've first isolated the red line from the front camera, color camera, and to find the center of it. Depending on the value of the center of the red line in relation to the center of the car, we adjusted the front wheels for the red line to be in the center.
We also have to adjust the speed depending on where the car is on the track. For example, if it goes down the ramp too fast, it might fly off. We have an update speed function for this. Finally, if we see a large green cone in the camera, we will stop the car.
And you might be wondering how successful our code is, so we've prepared a demonstration of our car doing the course.
So what would we do if we had more time? We would make the whole course bigger. That means more speed, steeper ramps, and larger loops. The bigger, the better. Thank you so much for watching our presentation. If you have any questions, please list them below.
Thank you so much. So now we have Team 3.
This is SimCity, a model that represents the maze-like abyss of modern-day cities with colors to represent the many different roads and signs. Just like any city, SimCity has many paths that you can take to reach your destination, and other paths which will lead you off course. Today we will be demonstrating how a car can be programmed to automatically reach a desired destination from a set starting point.
The motivation for this presentation was to take a fairly simple topic within robotics programming and present it in an approachable manner. We will use this model city to showcase it. The car will begin at the entrance of the city and will attempt to travel the streets using color-coded road signs in order to reach the end ramp. In order to navigate the city, the car will use various sensors to determine a route for itself.
The methods we use to determine these routes are AR tag detection and line following. AR tags, which are basically rip-off QR codes, are markers that our car will scan to tell it what to do. Line following is exactly what it sounds like. It'll allow our car to detect and follow a line.
To perform the detection, the car will use a color camera and a depth camera, which are two sensors commonly used in navigation. While a color camera simply shows us what the car sees, the depth camera translates the car's vision into a map which contains the distance to each object in view.
The different roads in our city are defined by different colored lines. To detect them, our color camera will take a picture and search the image for occurrences of colors from a list of hues. If a color on the list is found, we'll create a border around its instances, allowing our car to see and follow the colored lines.
To follow the lines, the car will turn based on where the line is in the image. If the colored road is on the left side of the image, it'll turn left, and vice versa. Unfortunately, since there are multiple color roads to choose from within the list, we will use an AR tag to specify which color we should set as our first priority to search for.
Our AR detection protocol will allow us to look at the quote-unquote street signs to see which direction to take. To do so, we'll essentially take our color image and continuously scan for AR tags. Once it detects a couple AR tag patterns, it will choose the closest one using the depth camera. Then it will take the information it scanned from the AR tag to choose direction and color for our car, allowing a smooth ride.
So now let's see how the car performs.
Our car has now navigated through SimCity successfully using our depth and color camera sensors, demonstrating AR tag and line following application in the process. These simplified robotics concepts have proven successful for our model city.
Thank you so much, Team Owo. So next we'll have Team 3, who goes by Team 4.
Racecar Team 3 final group project, ball following.
So for our final group project, we decided to create a new race car level. In that race car level, we would have a ball that would move and bounce at the same time, and we would have a goal in which the car would be able to hit the ball into. Now, in order to create this level, we had to design the level in Unity. In order to create the ball, we used a sphere, and we also created a movable ball object in which we would be able to click on the screen in order to move the ball into that screen so that we could test our code to show that we can follow it. We also added physics to the ball using rigid body, which allows for physical manipulation. We also added a bounciness physics texture to allow the ball to bounce based on gravity. The physics engine was used to add a force to the ball in order to move it in one direction. And we also added a goal in which we 3D modeled, in which if the ball was in the goal, it would show the time taken to complete the level. We also added interaction between the player and the ball, in which a force would be added to the ball based on the acceleration of both the car and the ball.
So along with implementing the level in Unity, we also created code for the car to follow the ball. So in order to align the race car with the ball, we used proportional control in the x-axis. In order to adjust the speed of the car, we would adjust it by the position of the car relative to the y. And in order to program the car to bounce the ball into the goal, we'd have to once again align the race car with the ball, and then once it was close enough, we would move the car at a high speed towards the ball. Deeper look at ball tracking. So since the ball was the only object that was blue, we could use the color camera to track the ball. So we used the area of the ball and to adjust the speed. So if the area was really a large value, we would decrease the speed, and if the area was a small value, we would increase the speed. And so that would allow the speed to be adjusted. And in order to track the position of the ball, we would use the column of the center pixel of the ball, and based on its position relative to the center, we would adjust the angle. And since the LiDAR can only scan in one plane, we decided to not use it.
Here's a deeper look into our ball tracking. So in the Unity level, we could click anywhere on the screen, and that would put the ball in that position. And as you could see, the car goes to that position where the ball is, and you could also see how it slows down the closer it gets to the ball. So here's the final result. The ball starts bouncing right in front of us, and the car will drive slowly up to it the closer it is to hit the ball in the goal, and it'll also align itself while it's doing this. So as you can see right there, the ball went out of the center, so the car aligned it with it, and it's going to hit it into the goal right here, and we'll complete the level.
So we faced a couple of challenges while we were implementing our project. First of all, the Unity software itself. We had some background experience with it and game engines in general, but there was a lot that we needed to learn and figure out in order to implement our new level. Another challenge we faced was having to manipulate and keep in mind all of the physics variables of the ball, such as the bounciness and the coefficient of friction. We had to make sure we got these right in order for our car and ball to interact properly. Finally, we had to adjust the speed of the car relative to the ball's position in order to make sure that we were lined up effectively in order to hit the ball into the goal. The problem with this was that the ball was so large that it could cover up some of our sensors and occlude the goal, meaning we couldn't see the goal when the ball was right in front of us. And this made it kind of hard to align properly. Overall, we think our project was successful in that we were able to track the ball, follow it, and ultimately hit it into the goal. Given more time, we would extend this into a two-player game similar to the video game Rocket League, where two autonomous cars can play at the same time and try to score points on each other's goals.
Thank you for watching.
Yeah, thank you so much, Team 3/Team 4.
Hi, I'm Mike Wimmer.
I'm Saki Little.
I'm Aditya Bhatia.
I'm Nathan Vigasna, and we're Team Alpha 1.
So the issue that we're trying to address is often we have problems and challenges, and the solutions that we create don't generalize very well. So for example, we have instances of wall following here, where the car has to follow a wall to get to a destination. And we have sometimes organic looking walls and artificial looking walls, and we have narrower and wider paths. And when we create a solution to get through these, sometimes it doesn't go very well and work very well with other things. So how can we more effectively create a solution that generalizes well?
So how do we solve this problem? We can use artificial intelligence. We can use one of the wall following tracks and manually drive the race car in order to collect images where the race car should move forward, left, or right. In order to perform image classification, we use LiDAR images. LiDAR is capable of detecting objects completely around the race car, whereas the color and depth camera are only capable of seeing in front of the race car. This gives the race car more contextual information of its surroundings. Using these images, we can train a model to be able to make decisions on which direction it should move based on the features it perceives.
Humans can easily distinguish the differences between this sports car on the left and the sedan on the right. But how does a computer do the same thing? It uses artificial intelligence image classification to evaluate and identify unique features specific to each vehicle. For example, if an image classification algorithm was made for the sports car versus sedan problem set, it looks at features such as the sports car is much brighter than a sedan, or the sedan takes up more pixels, etc. The main question is, how do we use this to navigate the race car? Image classification is used for the race car to analyze the LiDAR data to help the car to make decisions. For example, this classifier could identify these LiDAR scans as commands for forward, left, and right. We were able to develop and use this to navigate the car through multiple different courses without changes in model code. The classifier can generalize to work in different situations it has never seen before, allowing the vehicle to navigate any walled track without requiring additional training of the model.
Behind the scenes, our image classifier works using a convolutional neural network. A neural network is a computing system that basically functions by using layers of neurons, which are modeled after the neurons in our brain. The beginning neurons are the input layer, which is the labeled images we're passing through. Then you have multiple hidden layers that perform the computations and recognize the patterns, followed by the output layer. The neural network uses weights, which are contained within the hidden layers and transform the input data, controlling how one neuron affects the others. The overall function of a neural network is basically to recognize patterns in the data that is inputted and classify those into a form that is usable for your purpose. So the more good data you provide the network and the more passes you take through the data, the more accurate your neural network will be. The GIF on this slide shows the overall process of an image classifier using labeled photos of a cat and a dog. As you can see, the photos get fed through a filter-like system, which is then used to determine whether they are currently seeing a cat or a dog based on what it has learned through the neural network.
So when it came to actually creating our neural network, we used the Python programming language and the TensorFlow open source library, which is a set of tools to assist in creating neural networks. And we collected our data actually from ourselves driving through the wall following lab. And at each frame, we took an image and classified it or labeled it as being left, right, or forward based on what we were doing at the time. So we used all the data, almost 12,500 images in total, to create the neural network, and TensorFlow helped us adjust each weight after each training pass. And after 10 epochs or 10 passes through the data of training, we are up to 95% accuracy of the algorithm estimating whether it's right, left, or forward based on an image. Now we have to test on real courses.
Finally, we ran the model and the results were exceptional. The model was able to generalize to multiple tracks that contain different features.
Thank you so much, Team 5 or Alpha 1. So now we're going to go into presentations created independently by specific students. These students all had a chance to work together on teams to pursue different ideas and projects. However, some students have specific projects that they wanted to work on independently on top of the teamwork that they've already been doing. So Matthew, we have Michael's video.
Hi, everyone. I'm Michael Rybalkin, one of the students lucky enough to be in the BWSI programs. I'm a rising senior at Central Bucks East High School, and today I'll be presenting a project I worked on during the past few weeks of the Racecar program. The project goal is to develop a mechanism wheel platform that students could use to explore alternatives to the more typical two-wheel drive race cars, and also to learn about the advantages, disadvantages, and uses of mechanism wheels. First off, what are mechanism wheels anyway? They're a type of tireless wheel. Instead of tires, they have a set of rollers attached to the rim of the wheel. Mechanism wheels come in pairs, and each wheel can push the car both forward and sideways. This mobility makes mechanism wheels ideal for many industrial and storage environments, especially ones that have flat floors and tight spaces that can't be accessed by typical wheel setups. The dream project would be developing a tangible mechanism wheel platform for the BWSI program. The closest feasible project to that would involve three main steps. First would be researching and selecting a commercial robot to use as a base for the Racecar platform. I've already done this, and I found this DJI RobotMaster S1, which comes with mechanism wheels and is well built. And it's also about the same size as the mini race cars that all of the students are currently using. Unfortunately, the S1's code is proprietary, so the only way to control the mechanism wheels is to hack into the robot, which is very time consuming. After that's been done, a small computing module needs to be integrated into the platform so students can write and run code on the mechanism car. I estimated that this project would take 2 to 3 months. However, I want to finish something before the end of the program, so I switched focus to the Racecar simulator. The simulator is a tool that all us Racecar students use to test our code in a safe and virtual environment. My goal is to give the Racecar students an opportunity to experiment with and learn about mechanism wheels, and creating a virtual platform accomplishes this. And it's also feasible within 2 weeks, which is the time I had to work with. The thing is, though, the simulator was built in the Unity game engine, and all the scripting for the simulator was written in the C# programming language, neither of which I was very familiar with prior to this year's Racecar program. So I learned C# and Unity as I worked. You can get a pretty good idea of my expertise with all that from the short video I recorded about halfway through Yeah, it's not very impressive, is it? But I kept at it, and here's a demo of my results. Here we are. We're in the simulator. So to sort of explain the controls real quick, on a mecanum wheel platform, each wheel is controlled by a unique motor. So we can control all 4 wheels independently. If we move all 4 wheels in the same direction, like if we rotate them all forward and backward, then the car will move forward and backward as it's expected to. But we can also do other things. Like we can rotate all the wheels on one side the same way, and then all the wheels on the other side the opposite way. And the result of this is that the car turns in place, as you can see here. There's one more configuration we can do to get some interesting results, and that's rotating opposite pairs of wheels in the same direction. So that'd be like rotating the bottom left and the top right wheels at the same speed, and then rotating the top left and bottom right wheels in the opposite direction. And this causes the car to sort of shift to the side like this. Of course, typical wheel arrangements can't accomplish this, so you can use this agility to access certain areas that typical cars can't. And so, for example, let's say a car is driving down this hallway here. This is a corridor that a typical car wouldn't be able to access because the corner is too sharp, right? And the gap is too tight. If you have a real, like if you have the mini race car go through an environment like this, it'll probably get damaged, or it will definitely encounter some trouble. It'll probably get stuck too. It's just not something you'd like to see. So here we can use a mecanum wheel platform to sort of get around this. So here I've oriented the car like so, and now I can move, oh, the wrong direction. I can move sideways. There we go. I can move sideways here, carefully so I don't crash. And now we're in this tight hallway that I couldn't access before, right? And now that we've reached the end of the hallway, we can now move sideways again until we are free. You can see my steering is pretty bad, right? Because this code is designed as a tool for students to use. The idea is that they can write code which controls each of the 4 wheels individually. And as a result, their control is much more precise than mine. It turns out that controlling 4 wheels with just one controller, pretty difficult, but this definitely wouldn't be an issue once students start writing their own code for the platform. So as for some next steps, that tangible mecanum platform is definitely, even though I didn't accomplish that during 2 weeks, because that's like a 2 to 3 month project, still definitely something I want to go after. It seems really fun. I'd also like to take a quick opportunity to thank the BWSI program staff for bringing me this wonderful opportunity of a program to all of us students. I'd also like to thank the wonderful TAs, especially Matthew Caligaro, who first developed the simulator and gave me the opportunity to create this mecanum car platform. Thank you. I hope you enjoyed this presentation.
Thank you so much, Michael. And now we'll be seeing a presentation from Anhad.
Hello, everyone. This is my implementation of the SLAM algorithm on the Racecar platform. So what is SLAM? SLAM stands for Simultaneous Localization and Mapping. It's a navigation technique that is commonly used in robotics. As the robot moves through the world, SLAM allows it to construct an understanding of its surroundings and then use that map to figure out where it is. It gives us a convenient way to integrate all of the data that is coming from our sensors and understanding things in the world context. So what sensors do we have to work with on the Racecar platform? We have a color camera, which is a standard camera. We have a depth camera that takes every pixel in the color camera and calculates how far away it is from the robot. We have a LiDAR, which takes a 360-degree scan around the robot and gives the distance of each point. And then finally, we have an IMU, which gives the orientation of the robot. There are some challenges with implementing the SLAM algorithm on the Racecar platform. First of all, there's noise in sensor readings and a low resolution of some of the sensors. However, the biggest challenges are spatial coherence and temporal coherence. Spatial coherence means that the SLAM map needs to be the same at the same point in space. As you can see, this map is not spatially coherent because when the robot returns to the same point, the map has rotated, making it useless for navigation. Temporal coherence means that the map remains the same at different points in time. As you can see here, if this cone switched from blue to red, it would completely screw up the navigation algorithm. The first step in implementing SLAM is to unify all of our sensor data. Currently, we have 3 different coordinate spaces that the sensors are using. We have image space, which is used by the color camera and the depth camera, and returned as XY coordinates or pixels on an image. We have polar space, which involves radii and angles, which are returned by the LiDAR as it scans in a 360-degree distance scan. But we can integrate both of these together into our top-down coordinate space, which is an XY coordinate space centered with the car at 0, 0. Everything here is in units of centimeters, and all of our sensors can create one understanding of the environment. So this is the result of our top-down view algorithm. You can see all of the colors in the camera that have their distances measured from the depth camera and then placed onto our 2D map. And as well, the LiDAR data is converted from polar to Cartesian and overlaid as well. So once we have our top-down view, we need to fit them together frame by frame and stitch them together into a world map. We use the ICP algorithm to figure out how these 2 sets of points fit together from each frame, from each frame. So this is the ICP algorithm in action. As you can see, the red pixels are the pixels from the previous frame, and the blue pixels are the points from the current frame. And the ICP algorithm is calculating exactly how they need to be rotated, moved, and scaled in order to match together. So once we have the transformation between the points from the previous and current frame, we can integrate these changes over time to get a robot pose. The ICP algorithm gives us a transformation matrix like this. And we can extract the robot position from it by starting with an initial robot position of 0, 0, and then adding to it the x and y components of the transformation matrix over time to get x of n and y of n, which is our position at frame n. To fit our puzzle piece of a 2D scan onto our map, we simply need to keep track of a running transformation like this, based on the ICP information. We start with the identity matrix like this, and we get k of n plus 1 by applying the transformation to k of n. And we can take the transformation for the current frame, k, and apply that to all of the points in our local view in order to fit them onto our world map. So in conclusion, this implementation has the basic elements of SLAM. As you can see here, it's constructing a map, and it is also localizing itself and plotting its path using the yellow points. However, the limitations of the software and hardware platform make it a little bit impractical. As you can see, there's a lot of noise in the sensors and the localization. The ICP often fails to compute the exact transformation between the points, and this causes errors in the localization. However, there are many improvements that we can make. We can reinforce the SLAM algorithm with techniques such as Monte Carlo localization and particle filter localization, giving a more reliable position estimate. We can also use a probabilistic ICP algorithm that has better convergence and noise rejection, which helps with some of the errors in our data. Finally, we can also implement a loop closure or graph solving algorithm that corrects data from previous scans based on new information. This helps with spatial coherence. And we can also corroborate our top-down SLAM implementation that relies mainly on LiDAR data with an RGBD SLAM implementation that relies on our color and depth camera data. By combining these 2 different sensors in this way, we get a much more robust solution that helps with temporal coherence. Thank you for watching.
Thank you so much, Anhad. Now, I just want to take this moment to say how impressed I am by all of the students' work. These projects were done in the matter of just a few days. And so to see such amazing results is very impressive. So congratulations to all the students on their team projects as well as their individual projects. Now we're going to be going into the time trials. I know the students have been waiting for this for quite a while. The time trials are a great way for students to show off their skills in programming and to try to go through a very challenging course. It's no easy task, I will assure you. So when students are able to complete the time trials, it's quite a feat. So we'll have 2 different types of time trials. One set will be based on the time it takes for a student to complete a portion of the course, of which there are 4 phases. And the final one will be a time trial for the entire course. So we'll be awarding students for doing the portions, but the great grand prize will be your ability to finish the entire course. Okay, Matthew, are you able to talk at all?
Yeah, thank you, Emmy. Are you able to hear me?
Yes.
Awesome. Okay, great. So thank you for that. I'm just going to start by walking us through the course so everybody understands what's going on here. The course really serves as a conglomeration of all the challenges that students worked on in the earlier weeks as they were learning to use the different sensors on the car to do different autonomous tasks. There we go. For the first portion of the course, the car is line following here. And you saw that there were AR tags there that were telling the car which colors it needed to follow. Every time that the car completes this portion of the course, it's actually re-randomized. So they can't just remember ahead of time what colors they have to find. They actually have to read those AR tags to identify which colors to follow and then identify the best path. In the second phase, they move on to the lane following section. Well, now there are two colored lines that they have to stay between. Once again, you see there's an AR tag here telling them to change into the lane following section, and the color is telling them the color again of the lines. When they get up to here, there's an AR tag, which serves as basically a turn signal. It tells them which path doesn't have the speed bumps. And so it's much more advantageous if they're able to read this AR tag and avoid the speed bumps. Because again, these are randomized every time, so they can't just pre-record which direction they should turn. The color then changes in the lane following section to indicate that they should probably take this turn a little bit slower. And then we move on to the third phase, which is cone slaloming. Here we have to pass the blue cones on the left and the red cones on the right. In order to do so, the students are using the color and depth cameras on the car. The color camera is what allows them to identify the cones, and the depth camera is what allows them to estimate how far those cones are away with stereoscopic vision. If they fail to pass any of the cones on the correct side, like we can see here, they incur a time penalty in their time trial run. The cones in certain places are also organized in gates, as you can see here, so it's twice as difficult. They have to pass both of the cones on the correct side, and the hill makes sure that their program is robust enough to handle, different gradients. And finally, for the fourth section, they're working on the wall following. This is where the LiDAR that you can see spinning on top of the car really comes in handy. You can see on the upper left corner of the screen the data that's being captured by the LiDAR. That 360 view is what allows the car to identify obstacles all around it. Once again, we have an example of an AR tag telling them how they can take a more advantageous path. It's more direct on the side that the AR tag is pointing. And then they exit out into the final stretch and speed across the finish line. Kobe will now be announcing the races.
All right, so we're going to kick off the time trials with Michael, Fardine, Hitanch, and Ali and Savita's team. All three teams are going through the line following, each with different colors. And all four are able to correctly pick up the line, take the fastest route, and are able to complete the first phase with Michael's car first, followed by Fardine, Hitanch, and Ali and Savita's team, all successfully completing the first phase. Next, we have Nitin, Aditya, and Sam's car. They all, again, correctly pick up the line and are able to get through this first phase, with Nitin's car in front and Sam and Aditya right behind. They have moved into the lane following with Nitin correctly reading the tag, moving over to the right, avoiding the obstacles. Same with Sam's car, same with Aditya's car. Looks like Nitin has successfully gotten the turn as well without falling off the cliff. And Sam is going through that turn now. And there we go. He is able to successfully stay on the cliff and finish the second phase. And lastly, Aditya's car has also made the turn. Awesome. And now he is going to finish up the last second phase. And there we go. With Nitin's car in front, Sam and Aditya right behind. And now next we have another set of cars. We have Emma and Lasya's team, Grace and Waja's team, Alex and Aditya. So all four teams have successfully read the AR tag, taken the right path, with Alex's car in front and Grace and Waja's car right behind his. And Emma and Lasya and Aditya have also completed the first phase. Alex has successfully read the right tag and got around the turn, as well as Grace and Waja's team, with Alex finishing first. And here we see Aditya and Emma and Lasya's team has also avoided the obstacles with the AR tag. Unfortunately, Aditya's car seems to have driven off the cliff, but still a very successful run, being able to read the tag and get through the lane following. And here we see Emma and Lasya's team makes the turn and is able to complete the second phase of the race car time trial. And now here are all the times for the first two portions of the time trial. And we have Grace and Waja's team about to go through the cone slaloming challenge. Out of all of the groups that submitted only codes for portions of the time trial and did not complete the whole course. It looks as though Grace and Waja's team were able to be the only team to successfully complete the cone slaloming. They are carefully weaving through the cones, passing blues on the left, the reds on the right. And now they are about to enter the phase in which they have to switch from slaloming through single cones and into gated cones. And we can see them get through the first gate, and as can be seen, they are incurring a time penalty by driving straight through all the gates. But regardless, in the end, they are still able to successfully complete the third phase. And similar to their team, here's Nitin on phase 4. His car was also the only car able to successfully complete the wall following portion of the time trial. And the roundabouts are successful. He is able to drive through them carefully. And now through the narrow corridor portion, he has to make these turns carefully, micro adjustments, don't hit the wall. And there we go. He is able to successfully get through the corridors, and now reading the AR tag, he takes the right turn, able to avoid all the obstacles. And now into the home stretch, racing to the finish line, speeding up. And, well, successfully able to hit the finish line. And there we go. And so now these are the times for the first 2 teams, and we have 3 students who all submitted full codes in hopes of completing the full course. So we have Sean's car out in front, being able to race past the line following with Evan and Mike's car right behind his. And both Sean and Evan have successfully made the turn, getting past all the obstacles and have headed into the cone slaloming, while Mike's car has taken the right turn, avoiding the obstacles. And it looks like Sean and Evan are successfully weaving in between the cones, being able to avoid incurring any time penalties as Sean enters in to the gated cones while Evan is right behind his. Mike is heading up into the turn around the cliff. Is he able to stay on? Yes, looks like he is successful. And Sean and Evan are racing through the cone slaloming, managing to not incur a single time penalty by passing through all the gates and slaloming through all the single cones very well, as Sean's car enters into the wall following phase. Mike's car is entering into the cone slaloming. And here we see Sean is able to get through the roundabouts successfully, and Mike's car is getting through the single slalom, while Evan is right behind Sean, also through the roundabouts. Sean has navigated through the narrow corridor and has taken the right turn on the AR tag for the fork in the road, while Evan's car is entering through the narrow pathway and has taken the right turn. And Mike has successfully weaved through the gates of the cone, while Sean's car has finished, and Evan's car is also in the home stretch and has completed as well. Now, Mike's car still does need to get through the wall following in order to be placed into the full course awards. And so here are the first roundabouts. Successful. Second roundabout is also successful, dodging the wall at the end. And here he goes. He's about to enter into the narrow corridor. Let's see how he does. Makes the first turn well, close to the wall, but perfect. There we go. Weaving left, weaving right. And he has made it through the narrow corridor. And now the AR tag. Yes, perfect turn, avoiding all the obstacles. Now, as he exits out of the wall of mazes, he has to get through this final stretch. And it looks as though he will be successful, boosting up the speed, racing towards the finish line. And there we go. A successful completion, with Sean's car coming in first, Evan's second, and Mike's third. And now we will take another look at Sean's run, just to highlight how successful his was. And he is able to weave into the right color, reading the AR tag, gets through the line following with no problem, enters into the lane following phase, gets the right read on the AR tag, no speed adjustments until now, is able to successfully stay on the course through the cliff without falling off, and has successfully completed the second portion, weaving through the single cone slaloms going through the double cones with no problem. He has entered into the gate portion of the slaloms and is going through the gates really well. Extremely impressive by not incurring a single time penalty, managing to pass every cone on the right side. And with the last 2 gates, his car is about to enter into the wall following phase, in which he has also successfully managed to run through with ease. And with the first roundabout coming around, he weaves past that one, weaves past the second roundabout, able to avoid the walls using the LiDAR on his car, and enters into the narrow portion of the corridor, in which his car goes through with no problem, gets the final read on the AR tag, able to get past all the obstacles, and at the end, with the home stretch in view, he's able to boost his car up, increase its max speed, and race through the finish line.
Thank you for the announcements, Kobe. Could we get a round of applause for all of our racers today?
Yeah, if you want to unmute so that they can hear you.
All right. It was, as Emmy had touched on before, this was a very difficult course. The students only had a few days to work on this. And so it's very impressive, especially to the students completed, but also to all the students who got the individual portions as well. Quite an accomplishment. Now, for this time trial, students were allowed to either work individually or in pairs if they chose. But this afternoon, you'll get a chance to see the power of the students when they're working in larger groups of 4 for the Grand Prix. So at the beginning of the closing ceremony, you can stop by and be able to see the Grand Prix race, where entire teams have been collaborating on single cars. And we'll get to see how even more successful the students can be when they work together in groups. With that, I'll hand it back over to Emmy.
So since we were able to go through the videos fairly quickly, I want to take this moment to allow any sort of Q&A type stuff. So if you had questions for the teams, for some of the individuals on their time trials, does Roman want to read off some of the questions that the TAs had?
All right, so one question I guess Team 1 had, the duck-sized horses, is were there any difficulties learning how to use Unity? And if so, would you mind explaining how you overcame them?
Yeah, so while we were learning Unity, it was a bit hard to get over a small learning curve at first, but we asked the instructors, especially Matthew, because he had a lot of experience in Unity, and luckily he was able to help, and we actually got to finish the Unity levels pretty fast before the first day ended.
Thank you. I guess I'll move on so every team can maybe have one question to answer. So I can move on to Team 2, the Honey Nut Cheerios team. A question for you guys. How much did you guys already know about 3D modeling? And additionally, could you explain the process of morphing the model through the 3 programs?
I'll take this one. So we didn't have that much experience in Blender and SolidWorks, but we watched a lot of tutorial videos and then learned right away. And in terms of how we got the models in the Unity, so in Blender and SolidWorks, we exported our loop and the ramp as a object file. And then in Unity, we just imported the ad set and dragged it onto the screen.
Thank you for your answer. And moving on, we'll go to Team 3, who likes to go by Team 4. What was the inspiration to choose this type of game? Additionally, what would happen if the ball was hit in the wrong direction from the goal by accident? Would there be any way to recover the ball?
As far as inspiration goes, I think the inspiration was partly because of the video game Rocket League. It has a very similar idea where you have a ball and you have a bunch of race cars. And also in real life, for the FRC program, for the FRC competition last year, there were balls in which we had to have, some robots had to follow. And so I decided to base our project off of that.
Awesome. That sounds great. And now we can go to Team 4, who goes by OWO. And a question for you guys is, what would you have to do to take into account if there are other cars, people crossing the street, or traffic lights in the city?
So for obstacles in the way, you would also probably have to keep in mind it's not a color detection issue, it's more of a depth detection issue. If you can detect that there's an object in front of you or an object beside you, and the issue here would be that the object is moving. So you would need to be able to register that there's an object that is within your range, even though it's coming in and out of your range based off of where it's moving. And you would have to have the robot make decisions based off of that, so that it would be able to effortlessly avoid any obstacles that suddenly show up in its radius while it's moving. So for that, you would need something to slow down and stop or to dodge. If anyone in my team would want to extrapolate, you can.
I think that was a very good explanation of what we would do to help with that issue.
Awesome. And now with Team 5, the Alpha 1 team, a question for you guys is, what does your code do when there is a completely different environment that you guys cannot generalize to, or it's kind of hard to generalize to? Is there any sort of fail-safe that is built in for the car?
Yeah, I can take this one. So that's a quite interesting question, actually. So what happens is the model will always predict something, whether it thinks it's correct or not. And we actually haven't put in a fail-safe yet, but we could probably put in one where if the confidence was less than this set amount, then just go forward or stop or what have you.
Awesome. Thank you so much for your answer.
All right. I'm sure that the other TAs have prepared questions.
Yeah, I will ask some more questions. I'm going to loop back around to Team 1. I was wondering, were you able to, did you try implementing the AR tags in real life?
Lacia, I believe you're muted.
We didn't have enough time to implement the AR tags simply because implementing the line following itself was really difficult because the camera itself had a lot of lag. So what it would do is it would have each frame, like every second it would update. So getting the line following working itself took us a lot of time. And AR tags, if it moves too quickly away from the AR tag, it probably wouldn't have the time to detect it.
Okay, but is this something you would probably be interested in working on if you had more time? However,
of course, obviously, if we had more time, we could probably implement more things. Also, again, if the camera lag could be fixed, we could have done a lot more.
Okay, moving on to Team Honey Nut Cheerios. We were wondering, how does the car know where on the ramp it is in order to adjust the speed accordingly so it wouldn't fall off?
I can take this one. Well, the car doesn't really need to know where it is on the ramp because it requires such great speed to actually get around it. We're really just following the line around the ramp rather than considering where we are on the ramp itself.
So do you move at a constant speed or does it ever change in certain parts of the course?
You can take it, Hitansh.
Yeah, no, we don't. If you saw our code, we had the update speed function or adjust speed function. So we don't. So we go out, we have to go out a little bit. We have to maintain the speed fast enough while going up the loop while also not falling off. So we change our speed depending on where we are, which we determine.
All right, sounds good. Moving on to Team OWO, we wanted to ask, what challenges did you face in the city different than normal line following?
In this city version, in normal line following, we had you would just like set a priority of colors and then follow the lines based on that priority. So like red would be first, so you would go to all red lines and like green lines, then blue lines. But in the case of the city, we wanted to base it off of AR tags to set the priority. So that way it would choose based on based on what the tags told it to do. So we faced some challenges in that the AR tags were like spread across the city, so there would be multiple tags in frame. So we had to basically tell the program to prioritize different AR tags as well. So that was a challenge that we managed to fix by cropping the image to the biggest AR tag it sees. So that way it only chooses that AR tag, which then will tell it which priority to choose for the colors.
Yeah, and it seemed like it worked great. So I'm going to mix up the order, and I'm going to ask Michael a question. We were wondering, what was the original inspiration for trying to make the wheels? And do you plan on working more with BWSI to implement these wheels into the course?
Yeah, sure. So my inspiration for the whole Mechanism wheel platform is simply that
I was just aware of the DJI program before enrolling in the BWSI program, right? And while I was working on the car here last year, I was at the program in person then. I thought about how a mechanism wheel platform could also be viable in a lot of the situations that we were exploring then. And that was sort of how the idea came to me of making a mechanism wheel platform. And as for like working with BWSI in the future, I'm not sure if I can like answer this because I haven't like this isn't like anything official like that. But I mean, I'd love to do something like that in the future.
Great, and we look forward to it. So looping back to Team 3, aka Team 4, we were wondering what happens if the ball were to bounce out of view or maybe behind the car. How would the car respond and adjust itself to complete the goal?
So what we did, because of time constraints, we didn't really have a solid idea for that. But when the ball was out of frame from the color camera, we basically set a slow enough speed so that the car doesn't move past the ball. And in the future, if we had more time, we would probably implement like a search state where if the car had moved past the ball, we would make the car like turn around until it finds the contour of the ball.
Another question for Team 5. We were wondering if the process that you used for your car, is it similar to how, do you know if it's similar to how self-driving cars learn to drive?
There's a lot of techniques that they use, but one of the main differences between what we did and what they do is we only focused on using one sensor since you have our time constraints, while the other real self-driving cars use a whole host of sensors and manage to learn and train off all of those. So that's one of the big differences.
Yeah, sort of to add on to that, another difference is we were only able to collect training data from one certain course because in that course, we only had like 3 courses total. So we collected training data from one course and then applied it on the other courses. While with self-driving cars, they collect training data on a whole bunch of stuff and so much data to make it a lot more reliable.
Yeah, and I guess I can also kind of extrapolate on that as well. I think the main basis of mainly driving the car around to collect data and then training a model on it is almost merely the same. And then, like Aditya and Safi were saying, just the different sensors and only one training set, and that's basically the main differences.
Okay, thank you, Team 5. We have a couple questions for Anhad. So first one is, what techniques did you use to combine the sensors to implement your top-down view algorithm before you implemented the ICP algorithm?
Yeah, so the main technique I used is called vectorization. This is pretty key to the entire solution because Python in general allows you to do a lot of things, but it's kind of a slow language. So since I was dealing with so many points, by using vectorization, I could convert some of that Python code to fast C++ code, and that allowed me to process the data more effectively, like when I had to transform all of the LiDAR data from polar to Cartesian coordinates.
All right, thank you. And another question for you as well. Do the improvements that you mentioned slow down the program in some way, or are they pretty efficient?
So I think some of the improvements I mentioned, like the Monte Carlo localization, which is an additional step after the SLAM algorithm, I think that will cause some performance issues. But one improvement that can be made just overall to improve performance would be to actually run some of the processing on the GPU, which is very good at parallel computation and handling large amounts of data.
All right, thank you so much.
Thank you so much for your questions. I think it's actually about time that we head back. Sorry to cut you off, Alina. Thank you so much for the questions. Thank you all for coming to the Racecar session. I'm very proud of all the results we've seen and really excited to see who is able to win and just to see generally how people are completing the work.
Welcome, everybody. To start off this closing ceremony, we're going to begin with the Racecar Grand Prix. Now, in the Racecar course, students have been interacting with their cars in 2 different platforms. Every student was sent a physical car that they've been programming, and students have also been working in a simulation environment throughout the course. Now, the Grand Prix is one of the oldest traditions associated with BWSI, and usually it's held in person with physical cars, but that's not going to be possible this year. Over the last week, students have been working in groups of 4 to program solutions to the Grand Prix, and they've sent these all in, and we've run them on the simulation environment so you can see the cars competing. Welcome to the BWSI 2020 Grand Prix. In this course, students learned to write autonomous programs for both simulated and physical cars. For their final challenge, 6 teams have submitted autonomous programs to run in the simulated Grand Prix environment. For our first race, we have Team Alpha 1 on the left and Team Duck Size Horses on the right. Right out of the gate, Duck Size Horses taking an aggressive speed into that hairpin, but they successfully avoid the wall. Both of the cars are using the LiDAR that you can see spinning on top to identify close objects and avoid them. And it seems like both cars are doing this very successfully. No collisions so far. Duck Size Horses passes on to the lane following section, and Alpha 1 is close behind, doing so as well. Now the cars are using the color camera on the front of the car to identify the taped lines and stay in between them. Both cars seem to choose to take the left path. We'll see how that pays off for them. And now the change in the color identifies that they're entering the final turn. Both cars make it successfully. This AR tag tells the cars to return to a wall following, once again using their LiDAR to identify the walls and stay a safe distance away. Duck Size Horses choosing the left path. Let's see what Alpha 1 chooses. And it's left path for Alpha 1 as well. Duck Size Horses reducing speed as they get into the tight corridor. Let's see if Alpha 1 is able to use that as an opportunity to catch back up. The distance between them is closing. Let's see what happens next as they go under the bridge. And both cars are entering the next phase, cone slaloming. Now they have to pass the red cones on the right, the blue cones on the left. And Duck Size Horses is just doing an excellent job passing between these cones with no extra space necessary. And they're already on to line following. They read the AR tag telling them they have to follow the bright green line, and they're sticking to just that line, avoiding all the other colors. These line colors are actually randomized every time the course is loaded, so the cars can't pre-code the colors they need to follow. They actually need to read these AR tags to make the proper decisions. Speaking of which, Duck Size Horses is needing to read another AR tag, this time telling them which direction in order to take the more direct path. Looks like Alpha 1 is having some issues with the cone slaloming and they're being reset to the previous checkpoint. Ooh, and a collision for Horses. Let's see if they're able to recover from this. Seems like they're attempting to take a multi-point turn to make up for that collision, and it seems to be successful. They seem to be getting back on track. Meanwhile, Alpha 1 is taking another attempt at those cones. Let's see if they're able to get past the problematic cone from before. And it looks like they're able to do so. Alpha 1 continuing on to the line following section. And the finish line is in sight for Duck Size Horses. It looks like it's going to be victory for Duck Size Horses. Congratulations. Next, we have Team Owo on the left and Team 4 on the right. Team 4 taking an aggressive speed into this first hairpin, establishing an early lead. Team Owo seeming to take a more cautious pace, but doing a very good job of staying equal distant from both sides of the walls. Team 4 expertly navigating through the blocks, and they're reaching the hill, moving on to the lane following section. The AR tag tells them the color of the lanes, and they are off. Seem to be doing a pretty stable job of staying on between either sides of the lanes. Which side will they take? It seems that Team 4 has chosen to take the valley side. Team Owo reaching the hill as well. Soon they will be, just like Team 4, focusing on staying between the lanes. A little bit of air there for Team 4, but they're still staying between the lanes successfully. This change in color notifies them of the final turn, and they're successfully pointed towards wall following. Team Owo picking up some speed in the lane following section. Will they be able to catch up? Team 4 back into the wall following. They must make a decision, and it looks like they're choosing to go right here. Ooh, but a collision for them. Will they be able to recover? Team Owo taking the valley side as well with the lane following. They're coming into the final turn and taking it slow, but successfully. They're now pointed into the wall following section. Team 4 still stuck on the rock. Seems like they have not been able to recover yet. We'll see if Team Owo is able to pass them. This may be an example of slow but steady wins the race. Team Owo making the decision, and it seems that they will take the right path as well. Now this presents the danger, will they be able to pass Team 4 successfully? And they do. This next section we're going to accelerate for the interest of time, but Team Owo is successfully navigating through the corridor under the bridge, and they're into the cone slaloming section. Some very expert navigation here by Team Owo, leaving barely any extra space with those cones, just like we saw from the horses last time. And they're approaching the line following section successfully. We'll see if they're able to make the turn at the end, and it was unsuccessful. Now, unfortunately, Team Owo gets caught in a loop here, and they just keep missing that same turn. So neither car is able to successfully complete this race, so neither of them qualify for finals. For our final set of qualifiers, we have CB East to the left, Honey Nut Cheerios to the right, and the Cheerios are starting off with an aggressive approach into this first turn, establishing an early lead. Both of the cars expertly avoiding these obstacles using that LiDAR data to estimate how far away the objects are. Honey Nut Cheerios coming into the lane following section. And it looks like they intentionally reset themselves as they passed over the checkpoint. Maybe that's a strategy to make sure they're aligned as they go into the lane following section. Honey Nut Cheerios choosing to take the left path. CB East catching up into the lane following section as well. And that final color indicating to Honey Nut Cheerios they need to slow down to take that final turn. And they are back into the wall following section in the middle. CB East also choosing to take the left path through the lane following. And also successfully making that final turn. That is a pretty fast pace that Honey Nut Cheerios are taking through the sandstone section. Perhaps the fastest we've seen yet today, allowing them to establish a strong lead over CB East. Honey Nut Cheerios now working through the cone slaloming section. In this case, the cars use both their color and depth cameras. The color camera allows them to identify the cones, and the depth camera allows them to estimate how far that cone away is using stereoscopic vision. CB East coming into the cone slaloming section as well, and Honey Nut Cheerios are off into the line following section. The AR tag tells them they need to follow the color green, and they're staying tight on that green line. And it looks like they are not distracted by the blue or red lines. Will they make the turn into the wall following section? Yes, successfully Honey Nut Cheerios has entered the final wall following section. CB East is now working through the cone slaloming section as well. Seems like they're taking a more cautious pace, but they are staying nice and close to those cones, not wasting much distance. Honey Nut Cheerios coming into the decision, they read the AR tag and they successfully turn to the left. This tells them that they can take the bridges to avoid the detour underneath. Helps them shave off a few seconds. And they're coming into that final turn. This has been an issue for cars in the past, but they successfully make it. Honey Nut Cheerios coming into the final turn before the straightaway into the finish. CB East coming into the line following section as well. Looks like they're making it into that final wall following section. And Honey Nut Cheerios is inside of the finish line. It looks like it's going to be victory for Honey Nut Cheerios. Congratulations, you made it to finals. And now the moment we've all been waiting for, the final race. We have our two qualifying teams, Honey Nut Cheerios on the left, duck-sized horses on the right. And the horses are off to a fast start. And perhaps too fast, not quite making the hairpin turn. Honey Nut Cheerios use this opportunity to take the lead. But the duck-sized horses are able to recover, it seems. The question is, will this be too much of a setback, or will they be able to catch back up to the Honey Nut Cheerios? The Cheerios taking a rapid path through the lane following. Wow, this might be the fastest time we've seen through the lane following yet today. And the Honey Nut Cheerios are already onto the wall following section. Very impressive times for them. Not to be forgotten, the duck-sized horses are at this point through the wall following section and onto the lane following section, hoping to make up some lost time. Honey Nut Cheerios under the bridge coming into the cone slaloming section. We'll see if the horses are able to catch back up. Honey Nut Cheerios now entering into the cone slaloming section, and the horses coming into the second wall following section. And the Honey Nut Cheerios are on to the line following section. They read the AR tag, they seem to identify that they need to be following a red line, and they're staying right on that line, ignoring all the other color detours. And with that, Honey Nut Cheerios are already onto the final wall following section. It's looking very good for them. Seems like a bit of a mishap from the horses, but they are able to righten themselves. That is definitely something that they've shown. They are persistent. They're not stopped even when they miss a turn. And the Honey Nut Cheerios successfully identify the final AR tag, taking the more direct path. Let's see if they can make these last two turns. It's looking good. And the Honey Nut Cheerios come into the final hairpin. Duck-sized horses coming into the cone slaloming section, expertly navigating between those cones. And the finish line is in sight for Honey Nut Cheerios on the final straightaway. It looks like it's going to be victory for Honey Nut Cheerios. Congratulations to all of our racers today. Can we get a round of applause for our two winning teams, Duck-sized Horses in second place and Honey Nut Cheerios in first place? Great job to both of them and to all the teams who competed today. Thank you for watching and have a great rest of your afternoon.